All right, we back. Let's see. I forget where I left off here. Guess we can just start from the top of this page. This is the cache, just same diagram introducing the cache between the registers and main memory. For example, disk drive, read that. Similarly, a typical register file stores only a few hundred bytes of information as opposed to billions of bytes in the main memory. However, the processor can read data from the register file almost 100 times faster than from memory. So it's 2 orders of magnitude, like I said. Even more troublesome as semiconductor technology progresses over the years, this processor memory gap continues to increase. Processor memory gap. Why is that? It's easier and cheaper to make processors run faster than it is to make main memory run faster. Yeah, okay. I'll highlight that. I feel like that's an important thing to note. Memory bandwidth is the bottleneck for GPUs and CPUs. To deal with the processor memory gap, system designers include smaller, faster storage devices called cache memories, or simply caches, that serve as temporary staging areas for information that the processor is likely to need in the near future. Figure 1.8 shows the cache memories in a typical system. An L1 cache on the processor chip holds tens of thousands of bytes and can be accessed nearly as fast as the register file. A large L2 cache with hundreds of thousands to millions of bytes is connected to the processor by a special bus. It might take 5 times longer for the processor to access the L2 cache than the L1 cache, but this is still 5 to 10 times faster than accessing main memory. The L1 and L2 caches are implemented with a hardware technology known as static random access memory, SRAM. Newer, more powerful systems even have 3 levels of cache, L1, L2, and L3. The idea behind caching is that a system can get the effect of both a very large memory and a very fast one by exploiting locality. Tendency for programs to access data and code in localized regions. By setting up caches to hold data that are likely to be accessed often, we can perform most memory operations using fast caches. One of the most important lessons in this book is that application programmers who are aware of cache memories can exploit them to improve performance of the programs by an order of magnitude. You'll learn more about these important devices and how to exploit them in Chapter 6. There's a memory hierarchy. So we got registers, L1 cache, L2 cache, L3 cache, main memory, local secondary storage like an SSD, NVMe, remote secondary storage, distributed file system web servers. Okay, smaller, faster, and costlier per byte storage devices, larger, slower, and cheaper per byte storage devices. CPU registers hold word retrieved from cache memory, hold words. L1 cache was cache lines retrieved from L2, L2 cache from L3, L3 cache from main memory. Main memory holds disk blocks retrieved from local disks. Local disk holds files retrieved from disks on remote network servers. Storage devices form a hierarchy. This notion of inserting a smaller, faster storage device, e.g. cache memory, between the processor and a larger storage device, e.g. main memory, turns out to be a great general idea. In fact, the storage devices in every computer system are organized as a memory hierarchy. Similar to Figure 1.9, as we move up from the top of the hierarchy to the bottom, the devices become slower, larger, and less costly per byte. The register file occupies the top level in the hierarchy, which is known as L0. Or level 0. We show 3 levels caching L1, L2, L3 occupying main memory hierarchy as levels 1 to 3. Main memory occupies level 4, and so on. The main idea of memory hierarchy is that storage at one level serves as a cache for storage at the next lower level. Thus, the register file is a cache for the L1 cache. Caches L1 and L2 are caches for L2 and L3 respectively. The L3 cache is a cache for the main memory, which is a cache for disk. On some network systems, the distributed file systems, the local disk serves as a cache for data stored on the disk of other systems. Just as programmers can exploit knowledge of the different caches to improve performance, programmers can exploit their understanding of the entire memory hierarchy. Chapter 6 will have much more to say about this. Operating system manages the hardware. Back to our hello example, when the shell loaded and ran the hello program, and when the hello program printed its message, neither program accessed the keyboard, display, disk, or main memory directly. Rather, they relied on the services provided by the operating system. We can think of operating systems as a layer of software interposed between the application program and the hardware. As shown in Figure 110, all attempts by an application program to manipulate the hardware must go through the operating system. The operating system has two primary purposes. One, to protect the hardware from misuse by runaway applications, and to provide applications with simple and uniform mechanisms for manipulating complicated and often wildly different low-level hardware devices. Okay. Two primary purposes. One, to protect the hardware from misuse by runaway applications. Two, to provide applications with simple and uniform mechanisms for manipulating complicated and often wildly different low-level hardware devices. Operating systems achieve both goals via the fundamental abstractions shown in Figure 111, processes, virtual memory, and files. As this figure suggests, files are abstractions for I/O devices. Virtual memory is an abstraction for both main memory and disk I/O devices, and processes are abstractions for the processor, main memory, and I/O devices. We will discuss each in turn. Layered view of a computer system with application programs, operating system, processor, main memory, I/O devices. Abstractions provided by an operating system, process, virtual memory, files. Wonder why the graphic looks like that. Files, virtual memory, I guess, involves main memory and I/O devices, and process can access main memory and I/O devices. Okay, I can see how that diagram makes sense. Processes. When a program such as Hello runs a modern system, the operating system provides the illusion that the program is the only one running on the system. The program appears to have exclusive use of both the processor and main memory and I/O devices. The processor appears to execute the instructions in the program one after another without interruption, and the code and data of the program appear to be the only objects in the system's memory. These illusions are provided by the notion of a process, one of the most important and successful ideas in computer science. A process is an operating system's abstraction for a running program. Multiple processes can run concurrently on the same system, and each process appears to have an exclusive use of the hardware. By concurrently, we mean that the instructions of one process are interleaved with the instructions of another process. In most systems, there are more processes to run than there are CPUs to run them. Traditional systems could only execute one program at a time, while newer multi-core processors can execute several programs simultaneously in parallel. In either case, a single CPU can appear to execute multiple processes concurrently by having these processors switch among them. The operating system performs this interleaving with a mechanism known as context switching. To simplify the rest of the discussion, we consider only a uniprocessor system containing a single CPU. We will return to the discussion of multiprocessor systems in section 192. The operating system keeps track of all the state information that the let's go up to this call out here. I want to read this. Unix POSIX in the standard Unix specification. Aside. The 1960s was an era of huge complex operating systems such as IBM's OS 360 and Honeywell's Multics system. While OS 360 was one of the most successful software projects in history, Multics dragged on for years and never achieved wide-scale use. Bell Laboratories was an original partner in the Multics project, but dropped out in 1969 because of concern over the complexity of the project and the lack of progress. In reaction to their unpleasant Multics experience, a group of Bell Labs researchers, Ken Thompson, Dennis Ritchie, Doug McIlroy, and Joe Osana, began work in 1969 on a simpler operating system for a Digital Equipment Corporation PDP-7 computer written entirely in machine language. Many of the ideas in the new system, such as the hierarchical file system and a notion of a shell as a user-level process, were born from Multics, but implemented in a smaller, simpler package. In 1970, Brian Kernighan dubbed the new system Unix. Oh, I didn't know Kernighan dubbed it. I didn't know that he was the one that did that. As a pun on the complexity of multics. I knew about the Unix, like castrated multics. The kernel was rewritten in C in 1973. How do you even think of that? Take multics and say, oh, Unix, because it's a castrated multics. Like, how do you even get there? Yeah. It is amazing how some people's brains work. The kernel was rewritten in C in 1973, and Unix was announced to the outside world in 1974. Because Bell Labs made the source code available to schools with generous terms, Unix development developed a large following at universities. The most influential work was done at the University of California at Berkeley in the late 1970s and early 80s, with Berkeley researchers adding virtual memory and the Internet protocols in a series of releases called Unix 4.x BSD Berkeley Software Distribution. Concurrently, Bell Labs was releasing their own versions, which became known as System V Unix. Versions from other vendors, such as Sun Microsystems, Solaris Systems, were derived from these original BSD and System V versions. Trouble arose in the mid-1980s as Unix vendors tried to differentiate themselves by adding new and often incompatible features. To combat this trend, IEEE, Institute for Electrical and Electronic Engineers, sponsored an effort to standardize Unix, later dubbed POSIX. By Richard Stallman. I didn't know Richard Stallman dubbed it POSIX. Didn't know he was credited with that. The result was a family of standards known as the POSIX standards that covered such issues as the C language interface for Unix system calls, shell programs and utilities, threads, and network programming. More recently, a separate standardization effort known as the Standard Unix Specification, or SUS. I thought it was a single Unix specification, has joined forces with POSIX to create a single unified standard for Unix systems. As a result, these standardization efforts, the difference between Unix versions have largely disappeared. Traditional systems could only execute one program at a time, while newer multi-core processors can execute several programs simultaneously. Oh no, we already read that, sorry. The operating system keeps track of all the state information that the process needs in order to run. This state, which is known as the context, includes information such as the current values of the program counter register file and the contents of main memory. At any point in time, the uniprocessor system can only execute the code for a single process. When the operating system decides to transfer control from the current process to some new process, it performs a context switch by saving the context of the current process, restoring the content of the new process. And that's something I need to underscore, is that like most of my experience with context switching in the past like 5 years has been system calls where you context switch with the kernel. But there are, of course, instances where the kernel will get like an interrupt and it will actually suspend execution of the running process, save its state for it, and do a context switch to a different running process. That happens all the time. But for some reason, my mind doesn't apply the same term context switching to that concept, even though it's obviously appropriate. And something I was aware of, but I have that that synapse hasn't fully been reinforced recently. Okay, it performs a context switch by saving the contents of the current process, storing the content of the new process, and then passing control to the new process. The new process picks up exactly where it left off. Figure 112 shows the basic idea, for example, of hello scenario. So you have process context switching, you have process A and process B. Unicode. It goes into a syscall here, which is a context switch with the kernel. But I don't think you need a syscall to have a context switch between two processes. But anyways, you go into the read, jumps into kernel code, which then runs some process B, which then has a disk interrupt. Exactly. So this wasn't a system call. And then the kernel switch back to process A because it's reads complete and it returns from read. The two concurrent processes in our example scenario, the shell process and the hello process. Initially, the shell process is running alone, waiting for input on the command line. When we ask it to run the hello program, the shell carries out our request by invoking a special function known as a system call that passes control to the operating system. The operating system saves the shell's context, creates a new hello process, and in its context, creates a new hello process and its context, and then passes control to the new hello process. After hello terminates, the operating system restores the context of the shell process and passes control back to it, where it waits for the next command line input. As figure 112 indicates, the transition from one process to another is managed by the operating system kernel. The kernel is the portion of the operating system code that is always resident in memory. When an application program requires some action by the operating system, such as read or write to a file, it executes a special system call instruction, transferring control to the kernel. The kernel then performs the requested operation and returns back to the application program. Note that the kernel is not a separate process. Instead, it is a collection of code and data structures that the system uses to manage all the processes. Implementing the process abstraction requires close cooperation between both the low-level hardware and the operating system software. We will explore how this works and how applications can create and control their own processes in Chapter 8. Threads. Although we normally think of a process as having a single control flow, in modern systems, a process can actually consist of multiple execution units called threads, each running in the context of the process and sharing the same code and global data. Threads are an increasingly important programming model because of the requirement for concurrency in network servers, because it is easier to share data between multiple threads than between multiple processes, and because threads are typically more efficient than processes. Multithreading is also one way to make programs faster when multiple processes are available. As we will discuss in section 192, you will learn the basic concepts of concurrency, including how to write threaded programs in chapter 12. So if you go over here, what was the question I wanted to ask ChatGPT about? What is the name of Linux's threading implementation that came after Linux threads? Something like NLTP, something like that. And PTL, native POSIX threading library. So POSIX threads. So native POSIX thread library. Wait a minute. So NPTL implements POSIX threads. Are P threads the same thing as POSIX threads? Okay. So we use the P threads API, you're using POSIX threads. Oh, it's a glibc implementation. Since NPTL is glibc code, does that mean that Moosel has a different implementation of threads, P threads? Okay. So the way to remember this the way to remember this is it's P threads are POSIX threads, and the acronym is Native POSIX Threads Library. So I'm going to chuck that in my mind in that way. Because that acronym I've always had difficulty with, because it's just like what? Like NPTL? Like you can see like up here I was thinking like, what is this? NLTP? I got it reverse, except for the N. I got the N correct, but the PTL I got reversed. But I think I can remember it better if I just think of Native POSIX Threads Library, because it's P threads is the API, and I've used P threads API a bunch in the past like couple months, so I'm like, I'll be able to remember that. Okay, let's continue reading. So we got a diagram here, which is fun. Process virtual address spaces, similar to the diagram that's in the Linux programming interface. I like that they start from 0 and go up. I think that's the way to think about it. So you got the user stack created at runtime. Above that is kernel virtual memory, which I always wondered what is above the stack, because the stack isn't at like the maximum address. There are addresses above the stack, but it's like if you look at what is it, cat, I'll just do proc self maps. So the stack here, let me move this out of the way a little bit. So the stack is at this location here, and you can see a lot of the dynamically linked stuff is also like in a similar range, just 7F range. Only when you get to the heap and the actual, this is probably address space layout randomization, the reason why these addresses aren't at the bottom of the range. But you can see all the Fs. It says vsyscall. What is vsyscall? I need to learn what that is. What is vsyscall after the stack? And I'll give it the cat here. I'll do that, and then I'll do some dots here. vsyscall stands for virtual system call. It's a small fixed page in memory provided by the kernel that allows certain system calls to be executed in user space without a full, so it's kind of like the VDSO, but this is like an actual ELF thing that gets mapped in. This vstack thing, or vsyscall, I've never heard of this. We'll ask it, how does it differ from VDSO, which is also in the address space, just excluded from what I gave you. I thought that VDSO took care of that stuff, like get time of day, time, etc. vsyscall stands for a small fixed page in memory provided by the kernel that allows certain syscalls to be executed in user space without full context switching into the kernel mode. The original motivation was performance. On older Linux systems, calling get time of day, time, or get CPU involved expressive traps into the kernel. vsyscall allows these to be executed directly. It is mapped at a fixed high memory address near the top of the canonical 64-bit address space. Yeah, so it's pretty high up here, but even this doesn't go all the way up to the maximum. The size is 4 KB, just one page, memory page. It's executable, private mapping. You probably won't be able to write to it. Yeah, just XP. I don't know why it says copy and write if it doesn't have the ability to write, so not readable or writable from normal code. File offset 0, not backed by a real file system file. How it works: when you call certain system calls like so-and-so, the C library might just jump into this page. The instructions there execute a fast path in the kernel with a special mechanism, syscall instruction or int 80, depending on architecture, without the full kernel entry overhead. It's essentially a tiny trampoline for some syscalls. Why it appears after the stack. The address of vsyscall is fixed by the kernel, and in x86-64 it is always at this location. It's not related to your stack, it just happens to be high in the process virtual memory map. The stack is somewhere near the top of user space memory, while vsyscall is at the top of the canonical 64-bit address space reserved by the kernel. You see it after the stack and proc self maps, because proc self maps lists mappings in ascending virtual addresses. Modern Linux kernels have mostly deprecated vsyscall because it is unsafe. It's at a fixed address point, potential target for exploits. True. Modern kernels implement VDSO. Okay, there we go. So I actually don't need to send that query because it answered it here. Modern kernels implement VDSO, virtual dynamic shared object, instead, which is a readable, executable page in user space, providing similar optimized syscalls, but more flexible and safer. So in 2026 kernels, vsyscall exists mostly for backwards compatibility. Some syscalls may still jump to it, but usually the kernel maps a VDSO page elsewhere instead. If you want, I can draw a visual map. No, I don't need that. So I wanted to test it on a different program. So this was cat, but say I just had my own program like Vim chapter 01. Is there anything here? No. CP. We'll do LE01, and we'll grab the make file and the dot get ignore. Copy them here. Okay. And I'm going to say test pause .go.c. And here we're just going to do main and pause. And if I do a man to pause, that's in Unix standard.h. So I need to include that here, Unix standard.h. So make, build, there we go. And then over here I can say ps aux grep for pause, and that gives me back the PID here. And now I can cat out the proc PID maps of this, and that also has a vsyscall. So that's strange. Okay, well, I'm learning some things about VDSO and vsyscall. That's nice. So let's go back to the book though. We were looking at this diagram. So now we know the vsyscall stuff is up there, but it's also a bunch of other stuff. Our user stack, memory macro regions for shared libraries. Then we got a runtime heap going upwards. That's only if you're using a heap that's based on sbreak or break. And then you have your read-write data section, and your read-only and code data, and then yeah, program start loaded from the hello executable. Cool. Virtual memory is an abstraction that provides each process with the illusion that it has exclusive access to main memory. Each process has the same uniform view of memory, which is known as the virtual address space. The virtual address space for Linux processes is shown in Figure 113. Other Unix systems use a similar layout. In Linux, the topmost region of the address space is reserved for code and data in the operating system that is common to all processes. Let me restate that. In Linux, the topmost region of the address space is reserved for code and data in the operating system that is common to all processes. The lower region of the address space holds the code and data defined by the user's process. Note that addresses in the figure increase from bottom to the top. The virtual address space seen by each process consists of a number of well-defined areas, each with a specific purpose. You will learn more about these areas later in the book, but it will be helpful to look briefly at each, starting with the lowest addresses and working your way up. Our way up. All right, program code and data. Code begins at the same fixed address for all processes, followed by a data section that corresponds to global C variables. This does not take into consideration address space layout randomization, which I believe moves this somewhere else. The code and data areas are initialized directly from the contents of an executable object file. In our case, the hello executable. You will learn more about this part of the address space when we study linking and loading in Chapter 7. Okay. Heap. The code and data areas are followed immediately by the runtime heap. Unlike the code and data areas, which are fixed in size once the process begins running, the heap expands and contracts dynamically at runtime as a result of calls to C standard library routines such as malloc and free. We will study heaps in detail when we learn about managing virtual memory in Chapter 9. Shared libraries. Near the middle of the address space is area. Oops, sorry, I didn't advance here. Near the middle of the address space is an area that holds the code and data for shared libraries, such as C standard library and the math library. The notion of a shared library is a powerful but somewhat difficult concept. You will learn how they work when we study dynamic linking in Chapter 7. Stack. At the top of the user's virtual address space is the user stack that the compiler uses to implement function calls. Like the heap, the user stack expands and contracts dynamically during the execution of the program. In particular, each time we call a function, the stack grows. Each time we return from the function, it contracts. You'll learn how the compiler uses the stack in Chapter 3. Test stack recursion. .c main. Just want to answer this question, like how many stack frames can we have? This will be just void recurse, and we'll have a int counter 0, and this will be incremented counter plus plus printf %d new line comma that semicolon, and then we'll pound include our standard lib.h, our standard io.h, recurse. Okay, let's go ahead and build. Make, build. Test stack recursion. So we got to about 523,000. So about 500,000 call stack frames. And maybe we figure out the stack pointer. I don't like this, that it's split. Why did it do that? Stop doing that. How do you access the stack pointer in C? Okay, you have to write some assembly here. Kill that. Vim stack test stack recursion. So counter mod 100,000. We'll say that. No, we can't do that. Move the stack pointer into 0? What is %0? Oh, this is the void star that we declare as... Okay, that makes sense. Okay, so we declare the memory that we want to have access to, which is void star sp. And we do this little assembly trick here. To move that into there, that way we can print it out. And I'd rather it come first, sp like this. And then here we do %p. And do something like that. That should work, right? Make. Use of undeclared identifier. Oh, I have to. What? You say approximate stack pointer because it's gonna be near the stack. Just the address of local var. Okay, so we have to do this ugly underscore ASM. Huh? I just wanted to read the stack pointer. Okay, I'll do the stack trick. It's less cool. Int local. And we'll just get a pointer to local. Why is it core dumping like that? Counter is, if counter is less than 10. Oh, because we're just like, here, we'll do 500,000 here. 50,000? It literally crashes on that? Why would that segmentation fault? Counter is less than 10. Well, let's just take this pointer out here, because I had it going before. It's just the if, maybe? Oops. Still core dump. And then if I do this is what I had before. That didn't core dump. But eventually core dumped. So something with this or here. Can I just do or true? Or 1? Then %d. Okay. And then we'll do an ampersand local. We'll do okay. We got up to 261 there. Probably because of the extra stack space. So 200,000. Oh. Or counter is greater than. I said counter is less than 10 or counter is greater than 10. So it's just optimized away. It shouldn't even be like a that one optimized away. But like, what is going on here, man? I gotta GDB this thing. GDB. Build test stack recursion. We'll put a breakpoint on recurse and restart. No. Step into. Next. Step into. Sorry, step into. Next. Next. Step into. N S N N S S N N S N N. All right, we're at 9. So now if I P counter, it's at 10. So I'm going to step into recurse. P counter is still at 10. We'll do next. So it's skipping this one. That's fine. We didn't print. Step into. P counter should be 11. N. So it's 10. So it makes sense that that would get skipped. But counter is not getting incremented at all. Oh, okay. That's my bad. Quit, please. Yes. Yeah, that was my oopsie. I got a little carried away here. I just need to increment it up here. And then we'll do, okay, that's gonna make sense. 200,000. This is what I was considering this to be, which it wasn't because I was trying to be a little too clever. Okay. All right, let's go and run it. 2.6. We'll say 800 maybe. We'll do 700. Okay. So this is our base, basically. This would be the high number, and then we're going down and counting down. So if we do Python here, and I say, hey, you got this hex number, and you're going to subtract off this number, and that should give you your total size in bytes. It's only 8 megs, approximately. That's crazy to me. How large is the stack on a normal C program? Huh. I need to check the process stack limit with ulimit -s, ulimit -s. Hey, look at that. So that's probably in kilobytes. Yeah. Okay. So it's around 8 megs is the stack size, and the stack size on a thread is around 1/4 of that, which is 2 megabytes by default. Wow, Windows only has 1 megabyte. 7:30 already, damn. Okay, go away. Thank you. Let's rm leo1 a.out. Don't want that thing there. Alrighty, let's do some more reading here. Okay. I forget where we left off, but I'm going to start at shared libraries. Near the middle of the address space is the area that holds the code and data for shared libraries, such as the C standard library and the math library. The notion of a shared library is a powerful but somewhat difficult concept. You'll learn how they work. Yeah, we already read this. Stack. At the top of the user virtual address space is a user stack that the compiler uses to implement function calls. Like the heap, the user stack expands and contracts dynamically during the execution of a program. In particular, each time we call a function, the stack grows. Each time we return from a function, it contracts. You'll learn how the compiler uses the stack in chapter 3. It's interesting that they say it contracts and expands. Kernel virtual memory. The top region of the address space is reserved for the kernel. Application programs are not allowed to read and write the contents of this area or to directly call functions defined in the kernel. Instead, they must invoke the kernel to perform these operations. For virtual memory to work, a sophisticated interaction is required between the hardware and the operating system software, including a hardware translation of every address generated by the processor. The basic idea is to store the contents of the process virtual memory on disk and then use the main memory as a cache for the disk. Chapter 9 explains how this works and why it's so important to the operating system operation of modern systems. Files. A file is a sequence of bytes, nothing more, nothing less. Every I/O device, including disks, keyboards, displays, and even networks, is modeled as a file. All input and output in the system is performed by reading and writing of files using a small set of system calls known as Unix I/O. The simple and elegant notion of a file is nevertheless very powerful because it provides applications with a uniform view of all the varied I/O devices that might be contained in the system. For example, application programmers who manipulate the contents of the disk file are blissfully unaware of the specific disk technology. Further, the same program will run on different systems that use different disk technologies. You will learn about Unix I/O in Chapter 10. Chapter 10. Alright, learned a lot about that in the Linux programming interface. Systems communicate with other systems using networks. Up to this point in our tour of systems, we have treated the system as an isolated collection of hardware and software. In practice, modern systems are often linked to other systems by networks. From the point of view of an individual system, the network can be viewed as just another I/O device, as shown in figure 114. Let's look at 114 here. Okay, so we got CPU chip, register file, PC, ALU, bus interface, I/O bridge is all stuff that we were talking about before, and we just have a network adapter with the network. User types hello at the keyboard, client sends hello to a string to telnet server. Server sends hello string to the shell, which runs the hello program and passes the output to the telnet server. Telnet server sends hello world string to the client, prints hello world share display. Okay. When the system copies a sequence of bytes from main memory to the network adapter, the data flow across the network to another machine instead of, say, to a local disk drive. Similarly, the system call can read data sent to other machines and copy these data to its main memory. With the advent of global networks such as the internet, copying information from one machine to another has become one of the most important use cases for computer systems. For example, applications such as email, instant messaging, the World Wide Web, FTP, and Telnet are all based on the ability to copy information over a network. In August 1991, a Finnish graduate student named Linus Torvalds modestly announced a new Unix-like operating system kernel. Hello everyone out there, this is from Torvalds in Helsinki, Finland. Linus Benedict Torvalds. To the news group Comp OS Minix. Subject, what would you like to see in most of Minix? Summary, small poll for my new operating system. That'd be 25th of August 1991. I was 6 years old. It's crazy. Hey everyone out there using Minix. I'm doing a free operating system. Just a hobby, won't be big and professional like GNU for 386, 486 AT clones. This has been brewing since April and it's starting to get ready. I'd like for any feedback on things people like, dislike in Minix, as my OS resembles it somewhat. Same physical layout of the file system due to practical reasons, among other things. I've currently ported Bash and GCC and things seem to work. This implies that I'll get something practical within a few months, and I'd like to know what features most people would want. Any suggestions are welcome, but I won't promise I'll implement them. Linus Torvalds, as Torvalds indicates, his starting point for creating Linux was Minix, an operating system developed by Andrew S. Tannenbaum for educational purposes. The rest, as they say, is history. Linux has evolved into a technical and cultural phenomenon by combining forces with the GNU project. The Linux project has developed a complete POSIX compliant version of the Unix operating system, including the kernel and all the supporting infrastructure. Linux is available on a wide array of computers, from handheld devices to mainframe computers. A group at IBM has imported Linux to a wristwatch. That's not the craziest port I've heard of. Okay. Returning to our hello example, we could use a familiar telnet application to run hello on a remote machine. Suppose we use a telnet client running on our local machine to connect to a telnet server on a remote machine. After we log to the remote machine and run a shell, the remote shell is waiting to receive an input command. From this point, running the hello program remotely involves the 5 basic steps shown in figure 115. After we type the hello string into telnet client and hit the enter key, the client sends a string to the telnet server. After the telnet server receives the string from the network, it passes it along to the remote shell. Next, the remote shell runs hello program, passes the output line back to telnet server. Finally, the telnet server forwards the output string across the network to the telnet client, which prints the output string on a local terminal. This type of exchange between clients and servers is typical of all network applications. In Chapter 11, you will learn how to build network applications and apply this knowledge to build a simple web server. Oh, we got some mathematics. Important themes. This concludes our initial whirlwind tour of systems. We got some practice problems, concurrency discussion, and a summary. Okay, we're getting close to the end here. This concludes our initial whirlwind tour of systems. An important idea to take away from this discussion is that the system is more than just hardware. It is a collection of intertwined hardware and system software that must cooperate in order to achieve the ultimate goal of running application programs. The rest of this book will fill in some details about the hardware and the software, and it will show how, by knowing these details, you can write programs that are faster, more reliable, and more secure. To close out this chapter, we highlight several important concepts that cut across all aspects of computer systems. We will discuss the importance of these concepts in multiple places within the book. Amdahl's law. Gene Amdahl, one of the early pioneers in computing, made a simple but insightful observation about the effectiveness of improving the performance of one part of a system. This observation has come to be known as Amdahl's law. The main idea is that when we speed up one part of the system, the effect on the overall system performance depends on both how significant this part was and how much it sped up. Consider a system in which executing some application requires time t old. So some part of the system requires a fraction alpha of this time, and that we improve its performance by a factor of k. Consider a system in which executing some application requires time t old. Suppose some part of the system requires a fraction of alpha this time, and that we improve its performance by a factor of k. So it'd be multiplying it by 1 over k? Yeah, or dividing by k. That is, the component originally required alpha time, alpha t old, and it now requires alpha t old divided by k. The overall execution time would thus be 1 minus alpha t old plus alpha t old divided by k is now the new. So we can factor out t old, which is what we do here. So we got 1 minus alpha plus alpha over k, where alpha is the component the portion of the time that we're optimizing, and k is how much we optimize it. So if k is a really big number, then alpha drops to 0. If k is a very small number, alpha maintains its current value. in which case T old and T new will approximate each other. From this, we can compute the speed up S is equal to T old divided by T new. Speed up is T old divided by T new. T old would be T old. Okay, we factored out T old, so T old basically just gets eliminated because T old divided by T old. Okay, so that gets eliminated. Yeah, okay, that makes sense. As an example, consider the case where a part of the system that initially consumed 60% of the time, alpha 0.6, is sped up by a factor of 3. Then we get a speed up of 1 over 0.4 plus 0.6. Let's just walk through this example. As an example, consider a case where a part of the system that initially consumed 60%, so it's alpha 0.6, is sped up by a factor of 3, so k is equal to 3. We want this to be a huge number. Then we get the speed up of 1 over 0.4 plus 0.6 divided by 3. Which is equal to 1.67x, even though we made a substantial improvement to the major part of the system. Yeah, this is a huge part of the system, and it's a substantial improvement. We only got 1.67x speed up. Our net speed up was significantly less than the speed up of the one part. This is a major insight of Amdahl's law. To significantly speed up the entire system, we must improve the speed of a very large fraction of the overall system. Let's do a Desmos graphing of this so we can visualize it a little bit better. Desmos calculator? Yeah. So Amdahl's law would be S would be our speed up. So we want this to be our y-axis. So basically y is equal to 1 over 1 minus alpha plus alpha divided by x. Add slider for alpha. We need to set limits on this. 1, alpha is between 0 and 1. There we go. Go away, go away. There we go. So at best we can get linear. So when a is equal to 1 is 1 minus 1 is 0 plus 1 over x, which is just equal to x. Y is equal to x. So if we improve 2x, we're going to get 2x improvement. But you can see as we apply, and then how do you limit the bound of y? I think you say y is greater than, sorry, x is greater than 0. Yeah, there we go. And x and y, can I do y is greater than 0 here too? Maybe a comma here. There we go. Why is it? Well, if we jack it up to there, that seems to be working. Yeah, okay, good. So basically if A is 0, it doesn't matter if we get like 100x improvements. It's not going to have any change on it. And it say A is like at 50%. You get diminishing returns the amount of time you spend on speeding it up. I'd like to visualize this in 3D. I think Desmos has a Desmos 3D graphing. I think there's a 3D graphing calculator from them now. So I'm going to grab this, paste it in here, and I'm going to say A is 0. So if I want x, y, if I want to use terms that are A, oops, A, can I do that? No. So it has to be Z. Z is there, Y is there, X is there. So we want this view. X is greater than 0, Y is greater than 0, and we'll do Z is greater than 0. We do greater than or equal. All right. So this is the surface that we're looking at here. So if we look here, this is the no way. So why is there speed up? So we want to be in this area here. Can I do like a wireframe or something? I want to do a wireframe. Disable lighting? What does that do? No, I want a wireframe. Translucent surfaces? No. I want reverse contrast? No. Maybe over here? No. Alright, well, oh, no, A needs to be, we have to have our limits here. A needs to be between 0 and 1. Which means Z needs to be 0 and 1. There we go. Okay, so this is our surface here. You can zoom in a little bit. So you can see when A is low, it's very hard to get off that 1 there. And then when A is high, it's linear. It kind of twists that way. We zoom out a little bit. Can I draw a line on this surface that is like 50% of the system? It should be like this cross section here. So how would I do that? I think I would copy this whole thing, but I would limit the value of z to be equal to a specific value, which is 0.5. Oh, can I do that? By just saying z is equal to, I think I can if I say z is equal to 0.5. Wouldn't that work? No? Is greater than or equal to? And 0.5 is greater than or equal to. Maybe we do 5, 1 and 5, 0. Yeah, that's a pretty decent line there. We'll do like a little bit thicker here. We'll do like 4, 9. Okay. So that's how, oops, cancel. This is how you would, if you had 50% of your system that you're optimizing and you're able to get like a significant, like say like 4x improvement, that's the growth like curve. That's what it looks like right there. Basically, like you're kind of screwed. Like to get like a linear relationship, like you need to be close to 100% of the system. I might record a video on this. Let me do that, and then I'll just click start recording. I'll hide my webcam, and then I'll click start recording. Okay. Actually, let me stop the recording, and I should probably give this thing like a name instead of just being untitled graph. Oh, but I have to sign in. Let's go ahead and I don't want to sign in because I don't want to. Let me do that real quick. I'm gonna blur my screen and sign up for an account here. I'll be right back here. Let me plug this in. Okay. Let me go back to being live here. Oops. I'm not having fun right now. Important themes. Okay, I'm logged in. I want to hit save. Well, I'm just going to copy this just in case I lose it. And I'm going to hit refresh. Cancel. Log in maybe? Oh, I gotta log in. Give me 1 second. Alright, one more thing I have to do and then I can record the video. Let's do that and then we'll do that. There we go. Okay. Alright. So I have my thing. Let me make this a little bit bigger. We'll do 5.3 to 4.7. Maybe do 4.8 and 5.2. And then this will be like 75%. So we do 77 to 73. Let's do 74. 76. Okay, let's talk this over before I start a recording. So this is Amdahl's law. It computes, or it calculates the amount of speed up you can get from a given process where you optimize a fraction of the process called alpha by a amount called k. So for example, say like 50% of your system you're focused on optimizing and you optimize it 10x, say, as an example. And if you go over here and you look at the surface here, it's kind of janky the way it's rendering. There we go. But this blue this blue line on section of the surface here represents 50% of your system being optimized. I wanted to record a quick video here demonstrating some of the consequences of Amdahl's law. So Amdahl's law is something that I encountered in my undergrad, but I never really spent some time kind of playing with it. And since I encountered it in this book, the CSAPP book, I figured I would go through and explore a little bit this equation. So the equation is the speed up that you would get for any like optimization that you're doing is proportional to these two values, A and K, where A is the percentage of the process that you're optimizing, and K is the speed up that you get on that specific part of the process. So say like you're optimizing 50% of the process. Say you have a function that you're executing 50% of the time in your program, and you speed it up by 10x. So you might think that's a lot. It's half the program and you're speeding it by 10x. Like you should get like at least like a 5x speed up from that, right? No, that's not how it works. So I plotted this surface with all three parameters so you can see how these parameters affect the optimization. So this blue band here, basically I've limited it to be 50% of the process, or approximately 50% of the process. So if you focus on just 50% of your process and you optimize it by 10x, you're not even getting 2x speed up here. It's below 5 certainly, but it's actually around 2. And you can see like the progression, like if we zoom out here, like even if you get like 100x, like it's hard to see with this rendering here, but even if you get like say like 20x here, you're still limited by, what is this, like 10? Yeah, it's about 2, it's a little over 2 at this location. The Desmos 3D calculator is kind of glitching out a little bit because they got all these surfaces, but you can kind of see how that is. I kind of feel like I should re-record this because I'm not really doing it justice. Let me start a new recording. I'm reading the introductory chapter, A Tour of Computer Systems, from the Computer Systems, A Programmer's Perspective textbook. And they address Amdahl's Law really early on in the book, which is great because Amdahl's Law is something I encountered in my undergrad, but I never really spent any time with it, really. It's just something that was mentioned offhand as like a limiter in how you might optimize a process. So this statement here at the end of the section really jumped out to me. This is the major insight of Amdahl's Law. So this is the major insight. To significantly speed up the entire system, we must improve the speed of a very large fraction of the overall system. So let's kind of that's the insight, but let's kind of like take a few steps back. So what is Amdahl's Law? Well, it's this equation here. So it says the speed up in S of a given process is dependent on two variables. The first is alpha, and alpha is the percentage of the process that you're optimizing. And K is the amount that you've improved in the performance of that element of the did a very bad job at explaining that. I'm not even recording too. It would help if I record. All right. Let me try this again. All right, I'm recording now. So, how do I go about this? Do I just jump into Amdahl's Law and not even like give any context? I don't know. So I'm reading the Computer Systems, A Programmer's Perspective book, and the authors bring up Amdahl's Law really early on in the book, which is great because it is something that I encountered in my undergraduate, but I didn't really spend a lot of time with, like fully grokking. And I understood it had something to do with like the limiting of speed up that you would get from an optimization process. And I thought it was very coupled towards parallelism and concurrency, but I think it's just a general law. Having read this section, now I understand it's a general law that applies to optimizing any process here. And this statement is what really jumped out at me. It says, the major insight of Amdahl's law is to significantly speed up the entire system. We must improve the speed of a very large fraction of the overall system. So taking that statement, let's kind of work our way back a little bit to what Amdahl's law is. So Amdahl's law is this equation here. And it says the speed up that you would get from optimizing a system depends on two things. Alpha, which is the percentage of that process that you're actually optimizing. So you can imagine this being a function in your program. And speed, the entire process is like your entire program. So alpha would be like a function of your program that you're spending a lot of time in. And K is the amount of time that you're at, or the performance improvement that you get in that function, for example. So say you speed up that function by 10x, then K would be 10. And say that function is consuming maybe 50% of the runtime you're spending in that function, then alpha would be 0.5. So very straightforward parameters here. And you notice there's three parameters. There's two parameters and then the output of the equation. So we can plot that on a three-dimensional chart. So Desmos has this 3D graphing chart here, so I figured I'd do that. And this is the surface that pops out once you give it the appropriate constraints. And you can see when you're at the top, this goes from 0 to 1 for alpha. So 1 is 100% of your process that you're optimizing. So say you had one function for your entire program and you're optimizing the whole thing. Well, if you get, 100x speed up on that one function, well, that's going to be 100x speed up on your program. So that represents a linear relationship. So we can see that as a line right here. But as alpha decreases, you can see the results that you get are really poor. So the example I gave before with 50% of your function being optimized, that's this blue line here. So 50% as we're optimizing, we kind of hit this point of diminishing returns around, I would say around 2x here. If we zoom in, basically the amount of effort that we put into optimizing this part of the process now is giving us very poor returns. You get very, very poor returns at a certain point. And even at 75% of the process, we're still getting really poor results. So say we improve 75% of the process by 5x, we barely get like 2.5 x out of the 2.5x performance boost out of the entire process. So the big takeaway, which is what they said here, is that if you want to optimize a process, you really need to jack A up significantly. So if we go here, I have this is currently set to 75%. So if we go to maybe 95% here, I'll do 95, and just to make it easy to see here, I'll do 93. Oops, 93. So there you can see okay, we're focused on 95% of the process and we're optimizing it. Now the amount of effort that you put into it, you're actually getting a decent return as that value increases. But anything below 80%, the effort that you put into it is really, at some point, it's really not, the juice is not worth the squeeze. If we do maybe 79 here, yeah, I mean, you're still able to get a significant amount of performance improvement, but it definitely, it's it seems like a logarithmic relationship between the amount of effort that you put in and the actual performance that you get out. So very important law. I thought that was interesting. Thought I'd record a video on it. Cool. Okay, that was fun. I'm gonna save, and I will leave this because that was a 2D version. So I'll probably post that on YouTube, and I'm trying to get better at presenting ideas things that I learn as I learn them. And part of that is getting better at editing. I spent a couple of hours today, not only building, but building dependencies but also using the DaVinci Resolve on Linux. And it's a pretty sweet piece of software. I was able to get everything I wanted done. It's a very, very familiar piece of software if you're familiar with, Premiere or Final Cut or even After Effects. But yeah, I'm trying to get better at like presenting ideas, making it entertaining, and I guess we'll see how that one turns out. I'll write a little note here, make sure that I don't forget to edit it. Actually, I'll do it. Give me 1 second here. I know these big streamers, they got like a full editing staff. I am not that. Amdahl's Law video. Well, let me switch back over here. Bam. All right, let's continue reading. All right, a practice problem. Oh, we got to the practice problems. Good. It is 8:15. I probably should be winding down at this point, unfortunately. Suppose you work as a truck driver. Let's just read the practice problems. Looks like it's around Amdahl's Law, which is great. Oh, wow. We get into some concurrency stuff. Thread level concurrency, instruction level parallelism, single instruction, multiple data parallelism. Instruction level parallelism is where the CPU has multiple fetch decode units in front of a CPU core, I believe. Okay, I'm going to go ahead and just hop off here then. I don't want to stay up too late. I got gym in the morning, and let me show my camera. Forgot to pull that back over here. Where is the webcam? There it is. Oh, let me turn some light on too. Yeah, okay, so I'm going to hop off here. Tomorrow I'll pick up from where we left off with the practice problems. They seem to be related to Amdahl's Law around performance. And after that, there's like a couple pages on concurrency and parallelism, which I'm actually excited to read about. A lot of the stuff reading up to Amdahl's Law was very much a review, so I didn't really get much out of it. But yeah, I mean, it's an introductory chapter, so wasn't really expecting to get much out of it. Cool. So I'll go ahead and hop off here, and then tomorrow I'll be on. I have gym in the morning, and then I have a thing in the evening, but I'll be on after the gym in the morning to do some of the practice problems that we saw, and also I'm probably gonna take some time in the afternoon to edit that video that I mentioned. So cool. All right, I'll be on tomorrow. See ya. Peace.